Thank you for inviting me to this workshop, and good morning or good afternoon, depending on where you are. And since this is a workshop on unconventional computing, I thought that I would first motivate the talk by convincing you that magnetic devices are not really suitable for conventional Boolean logic type computing. And so then what would be left would be just non-Boolean computing. So that's the whole idea here. Now, as you know, that most signal processing architectures chips today are built with transistors. And the transistor is an excellent device. It has a high on-off ratio, which makes logic level restoration extremely easy. It has very low switching error probability, gain, isolation between input and output. And it's fast. You can switch a transistor in 100 picoseconds or less. But its shortcoming is that it's a volatile device. So it cannot store data in situ in logic gates. So you will definitely need to have some kind of a processor memory architecture. What you do is you do your processing or your computing in the processor, and you cannot store the data in the processor. So you have to send it over to some kind of memory where it is stored. And then every time you execute an instruction set, you have to bring the data back from the memory into the processor. So this back and forth going between the processor and memory, which is the bottleneck of von Neumann architectures, is what makes traditional computing based on CMOS type volatile devices inefficient. So this is why people propose nanomagnetic logic. So the good thing about nanomagnetic switch is that it's non-volatile. So you don't need to have a memory. You can store the data in situ in the processor itself, which speeds up the processing architecture. That's the pro, but there are lots of cons. The first con is that the switching error probability of magnetic switches is typically greater than 10 to the negative 9, whereas for transistors it is typically less than 10 to the negative 15. So there's a 6 order of magnitude difference in the reliability. A transistor is 1,000,000 times more reliable than a magnetic switch typically. Also, there are two types of magnetic logic, one that uses magneto-tunneling junctions and ones that do not. But if you use a magneto-tunneling junction, you know that it has a very poor on-off ratio. I think the world record is about 7:1, whereas for transistors, the on-off ratio is 10 to the power 5:1. So the transistor is 4 orders of magnitude better than a magnetic switch in terms of on-off ratio. So what does the poor on-off ratio do for you? What it does is it means that the off current is a significant fraction of the on current. So you have a very leaky device with a lot of standby power dissipation. And then finally, of course, ferromagnets switch very slow compared to transistors with 1 nanosecond switching time typically. But that is not a big deal because if you can do the non-von Neumann architecture, you might be able to compensate for the slow switching speed with better architecture. All right, so the next thing I want to talk about is that logic gates typically will have some fundamental requirements. There are actually about 6, but I'll talk about one, which is concatenability. What concatenability means that when you make a logic circuit, any sequential or combinational circuit, the way you do it is you take the output of one logic gate and then you fit it to the inputs of the next logic gate. And for this to happen, your inputs and outputs must be the same physical variable. So if they're voltages, they're all voltages. If they're currents, they're all currents. If they're light intensity, they're all light intensity. You cannot have dissimilar inputs and outputs. So I'll explain that with this thing. Let's say that one input to your logic gate is an elephant, and another input is hippopotamus, and your output is a tigress. Now you have a problem. The problem is that you cannot feed the tigress to the inputs of the next logic gate, because the next logic gate, one of them accepts only an elephant, the other only accepts a hippopotamus, and neither one would accept a tigress. So what you will have to do now is you will have to have transducers at every input port that will metaphorically transduce a tigress into an elephant or a hippopotamus. You cannot do logic like that. And no sane logic designer would build logic gates that are not concatenable. Okay, and so the problem with that is that these transducers, by the way, can be extremely complex. They can have very large footprint and they can consume a lot of energy. So they defeat the whole purpose of having energy efficient or small footprint logic gates if you have to have these transducers. But however, that has not stopped people from proposing logic ideas that are not concatenable. So here is one example. This is a 20-year-old proposal, room temperature magnetic quantum cellular automata. And it claims that it can implement 2 input and 1 output Boolean logic like AND, NAND, NOR, etc. The problem is that one input here is the sign of a magnetic field pulse. Another input is the phase of an oscillating field. And the output is the magnetization state of a chain of magnetic dots measured with magneto-optical Carr effect. I have no idea what kind of transducers will be needed to transduce the magnetization state of a chain of magnetic dots into the sign of a magnetic field pulse or the phase of an oscillating field. These would be extremely complex transducers. Of course, these proposals never mention this, but this is not practical. There is another one here, programmable computing. In this case, it also claims to make logic gates, but in this case, one input is the polarity of a current, second input is the polarity of a current, so these are similar, but the output is the magnetization state of a layer, which can of course convert into a resistance with an MTJ, and that can be converted into the magnitude of a current with a constant voltage source, and then you will need a current level shifter to convert the magnitude of the current to current polarity. So that is the complexity of the transducer that you will need at every input port. So these are again not practical. Now I did want to just specifically point out these two paradigms because there are many examples of non-concatenable logic proposals that appear in applied physics letters and other journals like that. I just picked this out, did 2 out because they appeared in marquee journals, Science and Nature. Here is another issue with magnetic logic devices. So as I said, that there are 2 types of magnetic logic devices, one that uses MTJs and one doesn't. And this is one that does not. So the good thing about it is that it uses bare magnets, which are not leaky. So you don't have a whole lot of leakage current. But the problem with these are that they're extremely error prone. So in this case, it was reported in this paper that the 1 out of 4 gates worked. So the error probability is 75%. Now, almost half a century ago, John von Neumann showed, this was a majority logic gate, by the way. And John von Neumann showed that the maximum tolerable error probability in a single majority logic gate is 0.0073. And if you have a circuit of logic gates, majority logic gates, then the requirement is more like 10 to the negative 15. So you need 10 to the negative 15, whereas here you have 75%. So that is not something that one can actually live with. I'm sorry, I cannot turn off that thing. Let me see if I can do that. Ignore that telephone ringing there. So, I mean, you have 15 orders of magnitude to go in this particular case, and that's not easy to do. So what you would end up with is a logic paradigm that has no reliability whatsoever. So these, again, are not practical. Here's another one that's quite famous. This is a single spin logic paradigm coming out of Purdue University. This one requires very complicated clocking scheme. And whenever you have complicated clocking schemes, you have the probability of high error. And then finally, this is one logic proposal that comes out of my group. We published that a long time ago. This uses skewed magneto-tunneling junctions. The skewed magneto-tunneling junction means that the easy axis of the soft layer and the easy axis of the hard layer are not collinear. They have an angle between them. And in this, and it can do NAND, NOR, etc., all of the universal logic gates. And in this case, we actually calculated their probability using stochastic Landau-Lifshitz-Gilbert simulations, and it turns out that the error probability at room temperature is 10 to the negative 8. It's still not good enough. The requirement is about 10 to the negative 15. So we are still about 7 orders of magnitude off. So the idea that I wanted to present here is that magnetic logic has 2 huge problems. One is that many of them are not actually logic ideas, are valid logic ideas, because they're not concatenable. And the second is that they're very unreliable. So, I want to very quickly talk about some experimental demonstration of a NOT gate in our group. So what we did is we built 2 magnets. And if they're dipole coupled, then they would tend to be antiferromagnetically ordered, which means that the magnetizations in the two magnets will be mutually antiparallel. So think of the first bit, the first magnet as your input bit and the next one as your output bit. And the reason that the input is more elliptical than the output is because of isolation. You want the input to influence the output, not the other way around. And in this case, if you just let it stay in the ground state, you will get the NOT behavior, that the output is the logic complement of the input. But what happens if you flip the input? If you flip the input, then you get into a situation where temporarily they're parallel. And now you would expect that the output would flip to assume the anti-parallel configuration, but it doesn't happen because in order to do that, you have to overcome the shape anisotropy energy of this magnet. So what you have to do is you have to apply stress. Stress, these are magnetostrictive magnets, by the way. So stress will rotate it by 90 degrees and then you relax and then the magnet flips such that it's anti-parallel. So this is how the NOT operation is realized. Stress acts like the clock to trigger the NOT operation. So we did this experiment. We built our nanomagnets here. Major axis is 200 nanometers, minor axis is 130 nanometers for this one, and for the other one, the minor axis is 80 nanometers. And these are MFM images of our NOT gates. And you can, if you are not familiar with them, think that the bright areas are like the north pole of the magnet and the dark areas are like the south pole of the magnet. So here with the magnetic field, we have magnetized them all in the same direction with the north pole always facing up. And then we apply stress and we see that at least in one pair, the NOT operation takes place, it flips. But the bad news is it's only 1 out of 9 that works. So the error probability is 88%. And that's obviously ridiculous for logic. You can't do logic like that. So we thought that in the previous experiment, we used cobalt nanomagnets, which are not very magnetostrictive. So we thought that maybe if we use a different material like iron gallium, which is 5 times more magnetostrictive than cobalt, we'll get better statistics. And we do, but not good enough. It's still 1 out of 4. So the error probability is 75%. But the good thing in here is that the energy dissipated for the NOT operation, we measured this actually, is only about 3 to 4 attojoules at room temperature. So it's an extremely low energy paradigm. Now I want to talk about something that is lethal for logic. And this is particularly true of in-plane anisotropy magnets, not so true of perpendicular magnetic anisotropy magnets. So in-plane magnetic anisotropy magnets, so when we are in academic labs, so in our academic lab, when you make magnets, they actually don't look very good. They have these rough edges or not smooth surfaces. And in the worst case scenarios, we can get things like this cratering, where you have a hole in the middle and then you have raised ridges around. And so these are magnets that people fabricate in academic labs typically. All right, so we wanted to see what effect these defects would have for in-plane magnets. So we model these as these kinds of defects, extended defects where you have thickness variation across a large region of the magnet, and then localized defects like a small hole or a small hill like that. And we simulated the magnetodynamics of these magnets with stochastic mu-max micromagnetic simulation. It takes a long time to run. Actually, it took about 3 months to run. And we calculated the error probability, switching error probability. And we found that in small, by the way, this was all switched with strain. And the reason we use strain-based switching is because it's very energy efficient. SOT and STT is much less energy efficient than strain. There is about 3 or 4 orders of magnitude difference in the energy efficiency. And we found that if you have localized defects, the error probability is not too high. But if we have extended defects like a ridge around, then the error probability is huge. The minimum error probability you get is 40%. So obviously you cannot do logic like that, okay? So the message that I want to leave here is that if you want to be both energy efficient and also reliable, you cannot do that. You cannot have both. So energy efficient Boolean logic is not viable because of the huge error probability. To my knowledge, there is not a single nanomagnetic logic chip in existence anywhere in the world, even after 2 decades. And there is no interest from industry, probably because they realize that it's not a viable technology. So once you have realized that, the only option that you have left is to go to non-Boolean computing. So non-Boolean computing, you heard the previous talked about neuromorphic computing with nanomagnets. And the example that everybody gives is the famous chess match between Garry Kasparov and IBM's Deep Blue computer. And the IBM won, the computer won barely, but the computer dissipated several kilowatts of energy, whereas Gary's brain dissipated only about 20 watts of energy. So neuromorphic architectures are supposedly very energy efficient. Not only that, but they're also forgiving of low on-off ratios because they're not logic, and they're also forgiving of high error rates simply because neuromorphic computing works on the basis of collective computation, where a single device doesn't really matter. Our neurons, many of them misfire, are faulty, but we can still work very well because the computation is based on the collective activity of many neurons and synapses working in unison together to elicit the computational activity. And so even if a few of them fail, it is not catastrophic, does not impair the circuit functionality. So the two things that neural networks will have to fulfill is that they must be extremely energy efficient, and they also have to have small footprints. So in my group, we actually studied this neural network. This is a very simple threshold neuron with synapses and weights. The weights can be implemented with resistors if they're fixed weights, and if they're variable weights, you can do them with MTJs also. And in this case, we simulated the firing characteristic of this neuron. Again, this neuron is built with, as you can see, with a skewed magneto-tunneling junction here. We simulated the firing characteristics of this neuron, and we compared our neuron with another similar neuron proposed from the Purdue University group. And what they proposed was using STT, whereas we used strain. And this is a simulated firing characteristic. So you can see that it's noisy because of the thermal noise. But ours is, the one, straintronic one, is less noisy than the STT-based one. But even more importantly, the energy dissipated in the straintronic neuron is only about 8 attojoules, whereas the one that is dissipated in an STT-based neuron is more than 3 orders of magnitude higher, 50 femtojoules. So we can make very energy efficient neurons with magnetic devices, especially if they're switched with strain or voltage control mechanisms that are more energy efficient than current control mechanisms. Another example of non-Boolean circuitry done with MTJs is an analog multiplier. So here what we have is we have this construct, and the resistance of the MTJ, if you plot that versus the strain generated voltage, they kind of look like this, and there's a region here where the characteristic is hyperbolic, which means that the resistance is inversely proportional to the applied voltage. So if you use that in this circuit, you can see immediately that the current output is the product of the two voltages, so you have an analog multiplier. The real multiplier actually looks like this. I don't have time to go through all of this, but these are the papers where you can actually read about all of that. So this is a single device multiplier. If you try to do this with CMOS, you will need 4 transistors, but here you can do it with just 1 device. So small footprint. Another one with a small footprint is a ternary content addressable memory. So here we have a skewed magneto-tunneling junction where the free layers z-axis and the hard layers z-axis are non-collinear, and their magnetization actually subtends an obtuse angle, not an acute angle. That's because the dipole interaction between the two layers would like to make them antiparallel, so they subtend the largest possible angle that they can. Now you apply strain, which will rotate the magnetization of the soft layer, but it will rotate clockwise. It rotates clockwise because they like to be antiparallel. So as they rotate clockwise, when the magnetization aligns antiparallel to this, you get the maximum resistance and hence the minimum current. And then if you go past that, the resistance again falls, and so the current increases. So now you can use this kind of a construct to make, with a single MTJ, you can make actually a ternary content addressable memory cell. If you try to do that with CMOS, you will need 16 transistors, but here you can do it with just a single MTJ. Next thing that, this is also well known, that we can do MTJ-based probability generators. You're going to hear a lot about P-bit-based computing in one of the next talks. So, one of the things that we studied is how to generate a probability distribution. using a voltage controlled magnetic anisotropy based MTJ, and this is the probability distribution. This is the VCMA voltage that's applied, and the probability of being 1, how that varies with the applied voltage. That means that the two are parallel, the soft layer and the hard layer are parallel. This is the low resistance state, and the 0 is the high resistance state when they're anti-parallel. And we actually simulate this in the presence of thermal noise and so on and so forth. So the restricted Boltzmann machine is a 2-layer neural network, which has a visible layer and a hidden layer. There are no intra-layer connections, there are only inter-layer connections, so you can update every layer at the same time. And we started this to do an image classifier, and in this particular case, this is all based on simulation, of course. The test or training sets are applied to the visible layer, and the hidden layers do the feature extraction, and we used from the MNIST set, a handwritten digit, this is 8, and we studied this, whether we can, using these constructs, we can actually predict the digit, and we can predict with more than 95% probability, and with very low energy dissipation. So this image classifier dissipates a 50%. Then the next question you want to ask is, are these computing applications, non-Boolean ones, also vulnerable to defects? And the answer is that the functionality is not impaired by defects. So it is much more reliable than Boolean logic, and I'll give you an example of that. So this is an example where we calculated the probability distribution of the 1s and 0s in an MTJ. As a function of, in this case, this was a spin transfer torque based switching as a function of current. And we varied the thickness of the magnet to see if we vary the thickness, does it change much? Well, if you vary the thickness, this is 5 nanometers, 6 nanometers, 7 nanometers. If you vary slightly, 1 nanometer variation, no big change. But if you go to 15 nanometers, which is 3 times more than the target, which is, of course, you'll never have that, then you see some variation. So what that tells you is that these probabilistic bit computings are very robust when you do them with magnets, unlike logic, which is very delicate, but probabilistic computing is extremely robust. So the functionality is not impaired, but the performance can be impaired. So when you do, for example, Boltzmann machines, you want to reach the ground state as quickly as possible. And how quickly you can reach the ground state depends on many things. So in this case, we started a binary stochastic neuron built with a low barrier magnet. And because the energy barrier is low, the magnetization goes all over the place, and the magnetization points in the northern hemisphere, you will call it bit 1, and in the southern hemisphere, you call it bit 0. So you need a thresholding function there. But anyway, the way that this thing, now let's say that you apply a current to fix the probabilities of 1. Say you want to fix the probability of 1 to be 0.3. How quickly can you do that depends on the correlation between the different magnetization states that you do. So we actually calculated this autocorrelation functions of this using stochastic Landau-Lifshitz-Gilbert equations, and you find that this one here, this is the defect-free magnet, no defects. And when you have this localized defects, like a small hole or a small hill, you don't actually change very much. But if you have non-localized defects like this ridge, then the autocorrelation function changes. So that means that the correlation time is sensitive to the defects. And that means, again, that things like performance, how quickly this can compute, that is affected by defects. But whether it can compute or not is not affected by defects so much. So, some of the settling times and things like that are also affected by defects. I won't go into that because I'm going to run out of time if I go into that. So let me just go into the next slide. So this is an example of doing image processing with nanomagnets. This is again all simulation. So in this case, the nanomagnets have binary states. They can either point up or point down, and these two states represent the pixel colors, black or white. And these are dipole coupled nanomagnets. And what we show here is that if there is a noisy image with mixed up pixels of black and white, and then you apply, these are all magnetostrictive magnets, and if you apply a stress, then what happens is that a black square will turn white if its majority neighbors are white, and a white square will turn black if its majority neighbors are black. So the region where the majority neighbors are white turns all white, and the region where the majorities are black turns all black. This is called edge enhancement detection. and is used to convert a blurry image into a sharp image. And you can do that with dipole coupled nanomagnets. And the good thing about this is that this is a hardware-based image processing. No software is involved at all. It's extremely fast, and the processing speed is independent of the pixel size. It doesn't matter whether you have 1 million pixels or just 10 pixels. It's always of the order of 1 nanosecond pixel processing time. So massively parallel hardware-based image processing, and the time is almost independent of pixel size. You could not do this with software. You can do this with this kind of hardware. Extremely fast image processing. The last couple things that I want to talk about is Boltzmann machines. So in this community, this should be well known that what you do is you have interacting neurons, and you want to make them go to the ground state, and the ground state represents the solution to the problem that you're looking for, the optimization problem or inference problem, whatever kind of problem that you're attacking. But the problem with the issue with this paradigm is that there is no guarantee that you will reach the ground state. You can get stuck in metastable states. And if that happens, you need something called simulated annealing to drive it out of the metastable state into the ground state. So algorithmically, simulated annealing is done with Metropolis algorithms, etc., which are very slow and don't guarantee that you will reach the ground state. So what we did was we did a very simple thing. So we built this is an atomic force micrograph of nanomagnets, and they're built very close to each other, so there is strong dipole interaction between them. And because of that, you can actually write the energy function of this array in the usual form of neural networks. This is your neurons, X is your bias vector. In this case, X is a vector of all elements are -1, and W is the weight matrix. And we isolated a 3x3 region here. And in this 3x3 region, you know that the ground state would be either this one or that one. So in the column, they're ferromagnetically aligned, all of them point in the same direction. Whereas along the rows, they're anti-ferromagnetic, they point in opposite directions. So you actually, we have 9 magnets here. Each one can be up or down. So we have 2 to the power 9 or 512 possible combinations. And we calculate the energies of all of these possible combinations. And indeed, we find that there are 2 low energies which correspond to this and that. So these are the ground states. Now we do this experiment. Now this is the AFM image of the system that we have. And you can see that they're actually in the ground state. In this column, they're all pointing up. In this column, they're all pointing down. And then we take a high moment MFM tip and we perturb the state, and they get stuck in this metastable state. Then we apply a surface acoustic wave, which is nothing but time varying strain, and it drives the system out of the metastable state into the ground state. And this is done with a surface acoustic wave, extremely low energy simulated annealing. So this is another application, hardware-based simulated annealing. It's extremely fast as well. The last thing that I want to talk about is an anti-correlator. So when you compute with p bits, you need to have a variable correlation or anti-correlation between 2 different p-bit generators. So we can do that actually with 2 MTJs that are dipole coupled, but we then apply strain selectively to one of the MTJs, and with this electrical pads. And what that does is it modulates the energy barrier inside the second MTJ. So if the energy barrier is too high, this is isolated from the other magnet because dipole coupling cannot overcome the energy barrier. And the best case scenario is this, when the energy barrier is just eroded but not inverted, and then you get almost perfect anti-correlation between the two, because if this is up, this is down, and vice versa. So we actually calculate the correlation function as a function of the stress that we apply here. And you can see that the correlation goes from no correlation to perfect anti-correlation. Perfect anti-correlation is -1. Okay? So this is a tunable anti-correlator, or you can make it a correlator also. If you don't place them side by side, but one on top of the other, you get a correlator, whereas if you place them side by side, you get an anti-correlator. And this is essentially a 2-node Bayesian network, where The first MTJ is the parent node, and the second MTJ is the child node, and the child state is affected by the parent, but not the other way around. So this is a directed graph, which is what Bayesian networks are, unlike Boltzmann machines, which are undirected graph. So, and this also, by the way, I don't have time to go into this, but it also generates conditional probabilities. So what is the probability of X being 1 given that Y is 0, and so on and so forth. For an actual implementation of a Bayesian network with this two integer structure, you can actually refer to this particular paper. This is going to take too much time for me to go through all the details here. But you can do Bayesian networks with simple MTJs and extremely energy efficient and quite fast. So in summary, nanomagnetic devices are not suitable for Boolean logic, despite the attractive feature of non-volatility, because of poor air resilience and low on-off ratio. So this is why we do unconventional computing or non-Boolean computing with magnets. So nanomagnetic devices can play a very important role in analog computing, which really doesn't care too much about low on-off ratio. Artificial neural networks, computing with p-bits, Boltzmann machines, computer vision, image processing, Bayesian inference engines, etc. And these applications are resilient, much more resilient against defects than logic. But the performance, that is how fast they can compute, can be affected by extended but not localized defects. So with this, I will stop. These are my collaborators and my students. And on the right, you see the funding agencies that fund this research. So thank you for your attention.